Okay, good morning, everyone. Before we start, I want to be sure that you can all hear me clearly. Please, can you all hear me clearly? Okay, thank you. So, we'll be starting now. Thank you, Shoki. We'll be starting now with data types. I think that is the next part. We did variables and mutability last week. So we're doing data types and proceed with the Starklings challenge. Okay. Okay, so proceeding to data types. Every value in Cairo is of a certain data type, which tells Cairo what kind of data is being specified, so it knows how to work with that data. Keep in mind that Cairo is a statically typed language, which means that it must know the types of all variables at compile time. The compiler can usually infer the desired type based on the value and its usage. In cases when many types are possible, we can use a conversion method where we specify the desired output type. Also, in Cairo, every variable every variable has a default data type called felt252. So if you do not specify the exact data type for that particular variable, it would adopt felt252 as its default data type, unless you have explicitly specified that this variable is not a felt252, it's a uint, it's a bool, it's something else. It will take up felt252 as its data type during compilation. So just to keep that in mind. So here is an example of a function main, and we are calling the x variable and specifying its data type. So to specify data type, you after the variable name, you append the colon sign, space, and then the type of data. If it's a felt252, if it's a uint, text2, if it's an array, if it's a tuple, if it's a struct, if it's an enum, whatever. It is appended after the colon and then the data type specified. And like I said, in Cairo, you cannot have a constant declaration without appending its value in Cairo. You cannot have a variable declaration for a const without appending its value. So like this is how a variable is being declared in Cairo. This is a variable name, the variable type, and the value appended to that variable. Now, what we are trying to do here is that we're trying to do a data type conversion. If you check here, this is felt252. Now, felt252 is the biggest size of of um, of a data. It's the largest size of a data. that can be assigned in Cairo. So if you are using field 252, if you want to compare to solidity, it's as if you are using Unit 256. It is the largest size of a variable. The largest size a variable can take in the memory in your compiler. So field 252 here is the largest size, highest size of a variable. Now, this is why called Unit 32. Now, field 252 also, that is where if strings are also classified under and other um, larger data types. So this is another variable called y, and it has the data type of unit 32. Now, unit 32 is very, very small compared to field 252. Field 252 can be seen like unit 256 or unit 252. And then this is unit 32. So what we are trying to do here is a type conversion. We want to convert x to a unit 32 because the value will not be more than unit 32. So instead of declaring it as a field 252, which will take more memory space for something that is not even up to the space in the slot, then it's better you append it to a data type that can contain all of its maximum numbers. Whatever will be the maximum amount that x will be, it's better to append it to a data type that can handle its max and minimum limit. So it is better you append it to a unit 32. And now to do that, you need to do a conversion. And to convert to a unit 32, we'll say x dot. We have these methods that helps us to do conversion, the into and the try into. We use try into dot unwrap for variables that have larger data type size. If you are trying to convert a variable with a higher data type size to a variable with a lower data type size, you would use this command, this macro, the try into dot unwrap, because it is larger than the size you are trying to convert it into. And that is why you use the try into dot unwrap. Your unwrap will have the the has the logic in case whatever you're trying to convert into is finally too small to hold what you are converting from. The unwrap will return the error for you or return success forever for you. So we use try into dot unwrap when you are converting from a larger data type to a smaller data type. If you are trying to convert from a smaller data type to a larger data type, you don't need to try into, because you know it will automatically, this larger data type can take whatever value the smaller data type has with space. So you just use into. But when you are typecasting from a larger data type to a smaller data type, you use the try into method. So that is what is going on here. We are trying to convert 3 from a field 252 to a unit 32. So you will see different type annotations for other data types. So scalar types. A scalar type represents a single value. Cairo has 3 primary scalar types: belts, integers, and booleans. You may recognize this from other programming languages. Let's jump into how they work in Cairo. The felt type. In Cairo, if you don't specify the type of a variable or argument, Its type defaults to a field element represented by the keyword felt252. In the context of Cairo, when we say a field element, we mean an integer in the range of 0 less than or equal to x less than p, where p is a very large prime number currently equal to 2 raised to the power 251 plus 17 times 2 raised to the power 192 plus 1. When adding, subtracting, or multiplying, if the result falls outside the specified range of the prime number, an overflow or underflow occurs, and an appropriate multiple of p is added or subtracted to bring the result back within the range, i.e., the result is computed mod p. The most important difference between integers and field elements is division. Division of field elements, and therefore division in Cairo, is unlike regular CPU's division, where integer division x over y is defined as this x over y, where the integer part of the quotient is returned. So you get 7 over 3 equal to 2, and it may or may not satisfy the equation x over y times y directly equals to x, depending on the divisibility of x by y. In Cairo, the result of x over y is defined to always satisfy the equation x over y times y, which is directly equal to x. If y divides x as integers, you will get the expected result in Cairo. For example, 6 over 2 will indeed result in 3. But when y does not divide x, you may get a surprising result. For example, since 2 times p plus 1 over 2 is equal to p plus 1 directly equal to 1 mod p, the value of 1 over 2 in Cairo is p plus 1 over 2 and not 0 or 0.5, as it satisfies the above equation. I hope we got that. Just a bunch of mathematics, but this is what um this is what felt 252 represents. It is this, the final number. If you do this, you would see that a very large number you get, almost 60 something characters or more. So as long as the value you get is not up to that or is within that, it can be contained in the field 252. And what would you do that will return that kind of extreme value in Cairo? So integer types. The field 252 type is a fundamental type that serves as the basis for creating all types in the core library. However, it is highly recommended for programmers to use the integer types instead of the field 252 type whenever possible, as the integer types come with added security features that provide extra protection against potential vulnerabilities in the code, such as overflow and underflow checks. By using these integer types, programmers can ensure that their programs are more secure and less susceptible to attacks or other security threats. An integer is a number without a fractional component. This type declaration indicates the number of bits the programmer can use to store the integer. So we can use any of these variants to declare the type of an integer value. If it's an 8-bit length, then it is under unit 8. If it is 16 bits, it's under unit 16, and so on and so forth. 256 bits is U in 256, 32 bits is U size. So anytime you see U size or unit 32, they mean the same thing. Each variant has an explicit size. Note that for now, the usize type is just an alias for Unit 32. However, it might be useful when in the future Cairo can be compiled to MLIR. As variables are unsigned, they can't contain a negative number. This code will cause the program to panic. This. So if you say x minus y, and here we are substituting 1 for x and 3 for y, it will return -2. And so it is going to cause the code to panic. All integer types previously mentioned fit into a FET252 except for unit 256, which needs 4 more bits to be stored. Under the hood, 256 is basically a struct with 2 fields. Unit 256 low, unit 128, and high, unit 128. Cairo also provides support for signed integers, starting with the prefix I. This integer can represent both positive and negative values, with sizes ranging from I8 to I258. I128, sorry. And each signed variant can store numbers from 2 raised to power n minus 1, from -2 raised to power n minus 1 to 2 raised to power n minus 1 minus 1 inclusive, where n is the number of bits that variant uses. So an I8 can store numbers from -2 raised to power 7 to 2 raised to power 7 minus 1, which equals -128 to 127. You can write integer literals in any of the forms shown in this table. Note that number literals that can be multiple numeric types allow a type suffix, such as 57 unit 8 to designate the type. It is also possible so you can read this up on your own. So this is int operations you'd expect for all the integer types: addition, subtraction, multiplication, division, and remainder. Integer division truncates towards 0 to the nearest integer. The following code shows how you would use each numeric operation in a let statement. So remember we said number literals can have their data type appended to them. So this is what it means. When you see something like this, what do you think this is? So when you see something like this, what do you think it is? Anyone from the house?
So repeat, let me see it again.
So when you see something like this, what do you think it is?
Is typing. You are typing the 5 to you 218.
Okay, cool. Someone else, Musraj, what do you think is going on there?
I think it's the data type. You're fixing it to
The
the data
data
type you
type.
want.
What?
Yeah, I think it's the data type. The U1.
What is the
So you're like
data?
setting it the U1 8, 1 to 8. So you're saying the summation of 5 and 10 should be in U1 8. So like you're aligning the data types together.
Okay. So we are saying, what we are doing here is same thing as saying sum colon U128 is equal to 5 plus 10. So we are defining that this 5 is of type unit 128. And this 10 is of type unit 128. So whatever this gives us, sum will always be of type 2128. That is what we're trying to say, declare here too. So addition, this is how you add number literals, and subtraction is the same, multiplication is the same, and division is the same. Result is 1. Okay, so for division, that was what it was trying to explain to us earlier when we're doing the Delta 252 stuff. So when you do division, what gets returned is the, you see that the result is 1. What it's trying to say is that it is just one time this 32 can go into 56. It will return the number of time it can go into the um what do you call this, numerator, right, and denominator. So if you say 56 over 32, it will return 1 remainder, whatever it remains. But what is going on here is that when you do division, division only returns how many times the process was successful. That means how many times 32 could go into 56. It will not return the remainder. That is what is going on here. That is what is going on here. It will only return 1. And if you minus 56, if you minus 32 from 56, you'd have what's left? You have about 24 left, which is smaller than 32. So it won't go into 56. And that is why your result that it will return is 1. So division is tricky also. Here, let quotient be 64 over 32. How many times can 32 go into 64? It's 2 times without any remainder. And that is why you see that the result is 2. So be careful and be conscious of this. Anytime you're doing a division, you should know what is going to happen, so um, you can work for possible errors that might align from doing that your computation in your Cairo code. Also, we have remainder. So just like the division returns how many times the denominator can go into the numerator, the remainder returns the remainder after the numerator has gone into the denominator. What is left? So 5 into 43 will go about 8 times, but can't go the ninth time because this is not 3, cannot, is smaller than 5. So 5 can go into 3. So what will return here is 3, the remainder. So for remainder, you use a percentile symbol called mode. So if you do a mode, the mode here returns the remainder. So that's why you see the result is 3. So don't get it twisted or confused. At this point, you are returning how many times the numerator, the denominator can go into the numerator successfully. While here is returning whatever is left after the numerator has gone into the denominator. Whatever is the remainder is what is returned here when you do this kind of computation using the percentage sign. So each expression in these statements uses a mathematical operator and evaluates to a single value, which is then bound to a variable. Appendix B contains a list of all operators that Cairo provides. So you can click here to see a list of the entire operators that Cairo uses. So we also have the Boolean type. The Boolean type in most programming languages has two possible values, true and false. Booleans are 1.252 in size. The Boolean type in Cairo is specified using bool. For example, let T be equals true. Let F colon bool be equal false with explicit type annotation. So using the bool F specified is you are declaring that F will always be a bool. So when declaring a bool variable, it is mandatory to use either true or false literals as value. Hence, it is not allowed to use integer literals, i.e. 0, instead of false for bool declaration. So for other, in other programming languages, or or what is it, machine language or so, that uses 0 and 1 to indicate true or false. In Cairo, you just use the true or false statement, not using the numbers, not using the integer to represent true or false. The main way to use Boolean values is through conditionals, such as an if expression. So we'll get to that. Also, we have string types. Cairo doesn't have a native type for strings, but provides two ways to handle them. Short strings using simple quotes and byte array using double quotes. Short strings. A short string is an ASCII string where each character is encoded on 1 byte. You can see there. So for example, A is equivalent to 0x61, B is equivalent to 0x62, C is equivalent to 0x63, 0x61, 62, 63 is equivalent to ABC. So Cairo uses FEL252 for short strings, as the FEL252 is on 251 bits. A short string is limited to 31 characters. So that is 31 times 8, which is equal to 248 bits, which is the maximum multiple of 8 that fits in 251 bits. You can choose to represent your short string with an hexadecimal value like 0x616263, or by directly writing the string using simple codes like this. So mind you, it is single quotes, not double, which is more convenient. Here are some examples of declaring short strings in Cairo. Let my first character be C, and let my first character in hex be 0x43. Let my first string be hello world, and let my first string in x be this. Byte array strings. With the byte array struct added in Cairo 2.4, you are not limited to 31 characters anymore. These byte array strings are written in double quotes, like in the following example. This is a string which has more than 31 characters. So if your string will contain more than 31 characters, it is better to declare it as a byte array. It's a long string and a byte array. And a byte array uses double quotes, not single quotes. You use single quotes for short strings, and you use double quotes for long strings. That is the byte array. We also, after talking about all these are identified under the scalar types. That means they have one value. Now we are going to compound types. So under compound data types, we have the tuple type. A tuple is a general way of grouping together a number of values with a variety of types into one compound type. Tuples have a fixed length. Once declared, they cannot grow or shrink in size. We create a tuple by writing a comma separated list of values inside parentheses. Each position in the tuple has a type, and the types of the different values in the tuple don't have to be the same. We've added optional type annotations in this example. So let soup be 10, 20, and true. For 10, we are assigning it a data type of unit 32. For 20, we are assigning it a data type of unit 64. And for true, it's you obviously know it's a data type called bool. So the variable toop binds to the entire tuple because a tuple is considered a single compound element. To get the individual values out of a tuple, we can use pattern matching to destructure a tuple value like this. Let 2 be 56, 2, and let xyz be equal to 2. So if y is directly equals to 6, print on a new line, y is 6. So what is going on here is, in case you want to get the individual values of, you want to just work with true and not everything, you can destructure this by appending them variables. So you can say let xyz be equal to this. Because you have 3 items in this tuple, xyz will take up each of the item according to their positions. So with this, you can now call z as bool and use it anywhere you want to use it. You can use y, you can use the x as independent variables after destructuring them. So that is what is going on here. Also, you can declare the tuple with value and types and destructure it at the same time. For example, you can say let x comma y be equal to 3252 to 3252 and be equal to 2, 3. So with this, you have achieved the structuring, you've achieved a tuple, you've achieved data type, type annotation, all in one line. So instead of doing it this way and then passing it a new variable name, you can do it this way where the tuple is already destructured upon assigning. So we have the unit type. Unit type is a type which has only one value, this. It is represented by a tuple with no elements. Its size is always 0, and it is guaranteed to not exist in the compiled code. You might be wondering why we would even need a unit type. In Cairo, everything is an expression, and an expression that returns nothing actually returns this implicitly. So this is for compound types. Now we are going to type conversion. So like I explained earlier, we have try into and into for type conversion. So either you're converting from a larger data type to a smaller data type, or from a smaller data type to a larger data type. So Cairo addresses conversion between types by using the try into and into methods provided by the try into and into traits from the core library. These are numerous implementations of these traits. Sorry, they are numerous implementations of these traits within the standard library for conversion between types, and they can be implemented for custom types as well. Into the into trait allows for a type to define how to convert itself into another type. It can be used for type conversion when success is guaranteed, such as when the source type is smaller than destination type. So what it means is that when success is guaranteed means if you are typecasting from a smaller to a larger, you know that it will be successful because the larger has the capacity to contain the smaller. So you use into um, for type conversion when success is guaranteed. So to perform the conversion, call var your into on the source value. So var here means the variable you're trying to convert, you're trying to typecast. So var.into on the source value to convert it to another type. The new variable's type must be explicitly defined as demonstrated in the example below. We have my uint8 as uint8, and we are appending 10 to it as the value. So now, if you want to typecast uint8 to uint16, you have to declare a new variable and you have to append the exact type of that variable that before you try the typecast, because it must have a new data type for it to be typecasted into. So to typecast this into a uint16, you append the data type to my uint16 as uint16, and you say my uint8.into with a bracket. If you are typecasting to uint32, my uint16.into, because now you've typecasted it to this and you are giving it this new variable name. So this way is the ways you can typecast using the into. Now let my felt 252 be equal 10. As a felt 252 is smaller than a uint 256, we can use the into method. So my uint 256 is equal to my felt 252.into. My other felt 252 is colon felt 252 is my uint8.into, my uint16.into. So what here trying to explain is, if you have a felt 252, you can also still use the into if you want to typecast it to a uint 256, because uint 256 has been added as a data type that is the largest currently, with 4 bytes higher than felt 252. So felt 252 can successfully be typecasted to uint 256. You can typecast any of these to a felt 252 because it is larger than all of these. And that is what is going on here. So this is how you work with the into method. Try into, similar to into, try into is a generic trait for converting between types. Unlike into, the try into trait is used for for-label conversion and as such returns option C. An example of a for-label conversion is when the target type might not fit the source type, the source value. Also similar to into is a process to perform the conversion, just called var.tryInto on the source value to convert it to another type. The new variable's type also must be explicitly defined as demonstrated in the example below. Let my uint 256 be a uint 256 be equal 10. Since a uint 256 might not fit in a FL 252, we need to unwrap the option T type. So to convert this into a felt 252, we'll declare the variable, append the felt 252 and say my uint 256 dot try into. Now the try into will not work without its macro, the unwrap. The unwrap is what will give you the option see where you have the value or the error. So when you do dot unwrap, it will make this expression stand successful. If it can convert to a FL252, it will convert, else it will unwrap the error for you. Same here, if you want to convert FL252 to unit 128, you do the try into dot unwrap, and so on and so forth. So this is how you do try into and into. This is how you do type conversions. And for a recap, for data types in Cairo, we have scalar and we have compound. So scalar are for single variables, for variables with singular values, and we have the booleans, we have the belts, we have the integers, where we have the unsigned integers and the signed integers, that is the int. And also we have the compound type, where we have the tuples that takes in different data types at once as one, and all the values also as one. We've seen how to destructure the tuple also, and we've seen how to do type conversion from a smaller to a larger data type and from a larger to a smaller data type. So far, so good. Do we have any questions to this point? So I guess there are no questions and we are all following. So let's do the quiz. So the largest number representable by the type int 128 is, so what is the largest number int 128 can have? What do you think, based on what we have done so far? So you have to remember the range of an int 128. So if you can remember the range of an int 128, you should know what the largest number would be here. So is anybody willing to help us? Are we still here? Hello guys, are you still here? Are you still with me? Hello. Oh, okay, cool. All right, so I guess we didn't get it. So let's go back to the int, explain it again then. I hope you should understand it by then. So this is where we explained the int. We said integers can represent both positive and negative values, with sizes ranging from int 8 to int 128. Each signed variant can store numbers from -2 raised to power n minus 1 to 2 raised to power n minus 1 minus 1 inclusive, where n is the number of bits that variant uses. So an int 8 can store numbers from -2 raised to power 7 to 2 raised to power 7 minus 1, which equals -128 to 127. So the largest number int 8 can store here is 2 raised to the power 7 minus 1, which is 127. So using this analogy, can you attempt this now? Can you tell me what is the largest number an int 128 can have? Okay. All right, yes. Because an int 128 largest number, it ranges from -2 raised to power 127 to 2 raised to power 127 minus 1. So 2 raised to power 127 minus 1 is the largest number a unit, an int 128 can have. So if x unit 8 is equal 0, what will happen when computing x minus 1? What will happen? Okay, so instead of cracking your brains, let us work this out. So let's say let x be x unit 8 be equal 1. You can say let y equal x minus 1. Okay, so y is 0. So let's run this. Okay, so we can see that the run panicked with this, and it said unit 8 sub overflowed. So it will always panic. Compiler will issue a warning about underflow. No, it will always panic. Let's just use this. So determine whether the program will pass the compiler. If it passes, write the expected output of the program if it were executed. So let's run this. Failed 32. Nice. So let's run it and see what this outputs. It's already screaming from here. Oh, lots of errors. First, it's screaming that there's no failed 32, type not found. So let's see. Does not compile. Okay, so you got everything correct. The largest number is this, and it will always panic is the correct answer to this. And then this will not compile because there is no data type called failed 32. So up to this point, guys, any question? Any question? All right, if there are no questions, unfortunately our time is almost up, just 4 minutes left. We cannot do the stack links today, but I can introduce you to it. But we'll start the stack links by next week. So this is Starklinks. You start coding. You can connect your GitHub if you like. So yeah. So this will be the introduction. Whatever you are asked, say welcome to Starklinks Cairo version 1. This exercise doesn't do anything yet, but it still compiles. Cairo file getting run needs to have a main function. So this file is a valid Cairo file. Other exercises will provide you to write code to make the exercise file compile. So we have function main. This is a valid Cairo code because it has the main function in it. So once you have included whatever it needs to be included, you click on compile. If it compiles successfully, it will return this. Then you can click next to proceed to the next level. So this is how Starklinks is. It helps you to learn the basics of Cairo. And if you successfully solve the entire Starklinks challenge, then you can consider yourself a successful Cairo um, developer. You can start writing your Cairo programs and your Cairo smart contracts and start building on Starknet. So this will be the end of the class today. If you have any questions, don't hesitate to ask. If you can't ask here, you can always ask in the group chat we created for this specific purpose. And with that, we'll be rounding up the class here today. So let me drop the link to Starklinks. Okay, Batipa. Um, the class has come to an end. Sorry. So I'm not sure you can transcribe as much as possible, but I would share the link to this Read AI so you can use that instead. So this is the Starklinks app. In case anyone wants to visit and get familiar with it and start writing Cairo code before we meet next class, it will be nice. I would highly advise it. So aside that, you all have a great weekend. Thank you for coming and bye for now.